Hi everyone, welcome to part 2 of the memory leaks in performance testing series. Before we dive in, a quick note. Over 60% of the viewers aren't subscribed yet. If you are enjoying the content, hit the subscribe button. Alright, let's get started. In part 1, we saw how memory leaks can bring down an e-commerce app during a sale. But before we dive deeper into detecting leaks, we need to understand where memory lives inside the JVM. So let's break down the JVM memory model, the heap, the stack, and the metaspace. When a Java application runs, the JVM divides memory into different areas. Each area has a specific purpose, and understanding these areas helps testers interpret monitoring graphs and detect leaks. The three most important ones for us are heap, stack, and metaspace. Heap is the place where the objects are created and live here. Stack is the place where the method calls and local variables are stored. Metaspace is the place where class metadata, methods, and constants are stored. The heap is divided into two major regions, young generation and old generation. Young generation is again divided into two different spaces, that is hidden space and survivor space. Young generation is for short-lived objects, whereas old generation is for long-lived objects. Here how it works. When a user browses the product in our e-commerce app, new objects like product and image are created in the hidden space. If these objects survive after a few garbage collections, they are moved to the survivor space and eventually to the old generation. Old generation is where leaks typically show because objects keep surviving and never get collected. So, if a cart object remains referenced after checkout, it will end up in old generation, slowly filling up the memory. Let's talk about the stack. Each thread in the application has its own stack. It stores method calls, local variables, and references. For example, when a user searches for iPhone in the e-commerce app, the search method call is pushed onto the stack. Local variables like search term is equals to iPhone live there. Once the method finishes, that frame is popped off and the memory is automatically released. The stack rarely causes memory leaks because the data is short-lived. However, deep recursion or unbounded thread creation can cause stack overflow error or thread memory issues. Finally, metaspace. Metaspace stores class definitions, method metadata, and constants. Unlike the old permgen, metaspace grows dynamically using native memory. In testing, leaks can also occur here, typically when applications load classes dynamically but never unload them. In our e-commerce example, imagine a poor configured plugin system where every time a new discount rule is applied, a new class gets loaded and never unloaded. Over time, metaspace fills and causing performance degradation. So why should performance testers care about heap, stack, and metaspace? Because monitoring tools show heap usage graphs and testers must recognize what's normal versus abnormal. Because most leaks happen in old gen and you will need to confirm this during analysis. Sometimes errors like out of memory error metaspace or stack overflow error might show up in the test logs. And you will need to identify them as memory issues, not the CPU or network issues. Understanding the JVM memory model bridges the gap between the test results and the root cause analysis. Now that you understand the JVM memory areas, the next step is learning how garbage collection works. Because leaks happen when objects escape garbage collection. In part 3, we will break down the garbage collector fundamentals, minor GC, major GC, full GC, and see how they impact the performance testing results. Thank you.